Hello everyone, I am Bireshwar Roy. I am currently pursuing my 4th year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question was asked in the JEST Physics paper 2019. This question is from the topic quantum mechanics. The question is, for a spin half particle placed in a magnetic field B, the Hamiltonian is H equals to minus gamma B Sy, which is equal to minus omega Sy, where Sy is the y component of the spin operator. The state of the system at t equals to 0, that is psi at t equals to 0, is plus state, that is upspin, where S-state operator operating on the plus state and minus state will give plus h cut by 2 plus state and minus h cut by 2 minus state. So here minus state is the down state, down spin. At a later t time, if Hz is measured, then what is the probability to get a value minus h cut by 2? The options are option A cos square omega t, option B sin square omega t, option C 0, and the last option D sin square omega t by 2. Let us see how to solve this problem. So it is given in the question, Hamiltonian of a spin half particle in a magnetic field B. The Hamiltonian is minus gamma B Sy, which is equal to minus omega Sy, where Sy is the y component of the spin operator. Now Sy operator can be represented as h cut by 2 times the Pauli matrix sigma y. So it will give h cut by 2 times the matrix 0 minus I 0. Now eigenvalues of the operator Sy is plus minus h cut by 2, and the eigenstates of the Sy operator are 1 by root 2 times the column matrix 1 plus minus I. Here plus sign is for upspin and minus sign is for downspin. Now the state of the system at t equals to 0 is plus state, so which is upspin state, which is given by 1 0. Now it is also given the Hz operator, that is z component of the spin operator Hz, acting on the plus state will give h cut by 2 plus state, and acting on the minus state it will give minus h cut by 2 and minus state, that is downspin. Now from the Heisenberg picture we can find the time evolution of a wave function if we are given the initial wave function at t equals to 0. So it is given by mathematically psi t equals to e to the power minus I h cap t by h cut times the initial state, that is psi at t equals to 0. Here h cap is the Hamiltonian of the system. In our case the Hamiltonian is minus omega Sy, which is also can be written as minus omega h cut sigma y by 2, and here initial state psi 0 is plus state, that is upspin. So we can write our wave function at time t psi as a function of t equals to e to the power I omega t by 2 times sigma y times the initial state psi at t equals to 0, that is plus state. So we can write it as e to the power I omega t by 2 times sigma y times the state, that is plus state. Now we will expand this exponential term. So after expansion we will get e to the power I omega t by 2 times sigma y equals to 1 plus I omega t sigma y by 2 plus I omega t sigma y by 2 whole square by 2 factorial plus so on. We can take the even power and odd power terms separately, and we can generalize it into a series form that is given by summation of p equals to 0 to infinity 1 by 2p factorial times I omega t sigma y by 2 to the power 2p plus summation of p equals to 0 to infinity 1 by 2p plus 1 factorial times I omega t sigma y by 2 to the power 2p plus 1. So, this series contains all the even power terms in this expansion, and this series contains all the odd power term in this expansion. So, in the last slide we have seen in the expansion of the exponential term we have multiple terms containing sigma y, sigma square, sigma y cube and so on. So, we will see how these operators sigma y, sigma square and so on acting on the plus state, and we will use that in our final result. So, sigma y acting on the plus state will basically give this matrix sigma y 0 minus I 0 times this up spin state, that is plus state 1 0. So, after multiplication we will get I times 0 1 state, that is down spin state, that is minus state. So, it will give I times minus state. Now, sigma square acting on the plus state, we can write this as sigma y times sigma y acting on the plus state. So, sigma y acting on the plus state will give basically I times minus state. So, we can write it here sigma y times I times minus state. Now, sigma y acting on the minus state, we can write it as 0 minus I 0 times 0 1, that is minus state. So, after multiplication it will finally give plus state. Again, sigma y cube acting on the plus state, it will give I times minus state. So, we can generalize this operation as sigma y to the power p acting on the plus state will give I times minus state when p is odd, and it will give plus state when p is even. Now, we will calculate this operation, that is e to the power I omega t by 2 times sigma y acting on the plus state. So, we have obtained this e to the power I omega t by 2 times sigma y can be written as this sum of two series, that is acting on the plus state. So, we will have two terms here, that is summation over p equals to 0 to infinity times 1 by 2p factorial times I omega t by 2 to the power 2p, that is acting on the plus state, and other term is summation of p equals to 0 to infinity I by 2p plus 1 factorial I omega t by 2 to the power 2p plus 1, that is acting on the minus state. Now, sin omega t by 2 can be written in the expansion, that is series form, that is omega t by 2 time minus omega t by 2 to the power 3 by 3 factorial plus omega t to the power 5 by 5 factorial minus so on. So, if we want to write this expansion in a generalized series form, then it can be written as minus of summation over p to the p equals to 0 to infinity I by 2p plus 1 factorial times I omega t by 2 to the power 2p plus 1. Similarly, cos of omega t by 2 can be written in this series form, that is summation over p equals to 0 to infinity times 1 by 2p factorial times I omega t by 2 to the power 2p. So, we have e to the power I omega t by 2 times sigma y operating on this plus state. It will give these two terms that we have seen in the last slide. Now, this first series is basically our cos omega t by 2, and this second series is basically minus of sin omega t by 2. So, we can write it as cos omega t by 2 times this plus state minus sin omega t by 2 times this minus state. So, we have obtained our wave function at time t, that is given by e to the power I h cap t by 2 operating on this initial state psi at t equals to 0. So, it will give basically psi at time t cos omega t by 2 times plus state minus sin omega t by 2 times minus state. Now, the SZ operator acting on this time evolved wave function, that is psi at time t, will give basically h cut by 2 times sigma z operating on this psi t, that is cos omega t by 2 times plus state minus sin omega t by 2 times minus state. So, it will give basically h cut by 2 times sigma z will operating on this plus state will give 1. So, it will be cos omega t by 2 times plus state, and sigma z operating on this minus state will give minus 1. So, essentially it will give plus sin omega t times minus state. So, probability to get a value h cut by 2, that is the downspin upon measurement of Hz, that is probability of minus h cut by 2, is basically this mod square of this coefficient of the minus state, that is mod square of sin omega t. So, basically it will give sin square omega t by 2. So, our option D is correct. So, we have discussed this solution in detail, and we found that the Hz is measured at the final state, that is psi at time t, then the probability of getting minus h cut by 2 is sin squared omega t by 2. This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 1 mark. This question is from the topic quantum statistics. The question is, choose the correct statement related to the Fermi energy EF and the chemical potential mu of a metal. Option A is mu equals to EF only at 0 Kelvin. Option B, mu equals to EF at finite temperature. Option C, mu less than EF at 0 Kelvin. And the last option, option D, mu greater than EF at finite temperature. Let us see how to solve this problem. We know the Fermi distribution function in discrete form is given by the average number or the occupation number of the particles at the energy level EA is 1 by 1 plus exponential of EA minus mu by kBT, where mu is the chemical potential. Now, if we want to see the plot of this function, then we will get two nature of this function, that is at t equals to 0, it will be a step function. So, this function will have value 1 less than the energy EF equals to mu, and at t greater than 0 Kelvin it will be a decreasing function like this, and at mu it will have 50% occupation probability, that is it will have a value half. Now, let us choose a temperature very close to 0 Kelvin. So, at this temperature, this exponential term, that is exponential of EA minus mu by kBT, will tend to infinity plus infinity if our energy EA is greater than mu, and this exponential term will be very small positive value close to 0 if our energy level is less than our chemical potential mu. So, the average number of the particle, that is the occupation number, will be 1 if EA is less than mu, and it will be 0 if EA is greater than mu when the temperature is very close to 0 Kelvin. So, from here we can conclude that we get that at t equals to 0 Kelvin, that is absolute 0, the Fermi energy level is equal to chemical potential energy, that is EF equals to mu at t is equal to 0 Kelvin. So, our option A is correct in this case. So, for this question, the first option, option A, that is mu equals to EF only at 0 Kelvin, is the correct option. This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 2 marks. The question is from the topic solid state physics. The question is, consider a one-dimensional non-magnetic crystal with 1 atom per unit cell. Assume that the valence electrons, number 1, do not interact with each other, and number 2, interact weakly with the ions. If n is the number of the valence electrons per unit cell, then at 0 Kelvin, option A, the crystal is metallic for any value of n. Option B, the crystal is non-metallic for any value of n. Option C, the crystal is metallic for even values of n. And the last option, option D, the crystal is metallic for odd values of n. So, let us see which option is correct. So, here we are given one-dimensional non-magnetic crystal has one atom per unit cell. Let the atom have n valence electrons. Now, there are two assumptions we have to consider according to the question. Those are, there is no interaction between electrons, so no electron-electron interaction. And the second assumption is electrons have weak interaction with the positive ions, that is electron-ion interaction. So, these are the assumptions basically we consider in the root theory of metal. Now, we can have either even values of n, that is number of valence electrons per atom, or odd values of n. So, for even values of n, if we choose n equals to even value at T is equal to 0 Kelvin, these electrons will make either a covalent bond or van der Waals bond. Example, silicon, germanium, carbon, this type of atom has 4 or even electrons in their valence shell, and they make covalent bond with their 4 nearest neighbors. Now, the second case, odd values of n. If we choose odd values of n, then at T is equal to 0 Kelvin, the electrons will make either ionic bond or metallic bond. Since here we have only one atom in the unit cell, that is monoatomic basis, while bonds require two electronegative and electropositive atoms in the crystal. So, ionic bonds are not possible in our case. In this case, most favorable bond is metallic bond. In the metallic bond, the outer energy levels of metals atoms, the s and p orbitals overlaps. The electron participating in the metallic bond is not shared with a neighboring atom, nor it is lost to form an ion. Instead, the electrons form what may be termed as electron sea, in which valence electrons are free to move from one atom to another. Let us consider some example. Sodium, which has valence electrons n equals to 1, aluminium, which has valence electron n equals to 3, silver, which has valence electron n equals to 1, gold has valence electron n equals to 5. So, all these elements are basically metals having odd number of electrons in their valence shells. So, sodium, aluminium, silver, gold, etc. are few metals in which total number of valence electrons are odd. So, the one-dimensional crystal will be metallic for odd values of n, that is odd number of valence electrons in the valence shell. So, our option D is correct. So, we have solved this question and we found that the last option, option D, the crystal is metallic for odd values of n, that is the correct option.